Here we state Coulomb's law. If we have a charge Q1 and a charge Q2, and if these are point charges, now the hanging pieces of tape weren't exactly point charges, but if we use shorter pieces of tape, well, let's see why hanging pieces of tape aren't point charges. Okay. Now here are two pieces of tape. Maybe they still attract a little bit, but well, let's just make them act like they oughta. Okay, so they're attracted, certainly. Doesn't matter which end, they're attracted. But these aren't point charges. Some parts of the charge are near my finger. Let's take this one. Some parts of the charge are here near my finger. Some parts are down here at the other end. And similarly on this tape, charge is distributed from one end of the tape to the other. Okay, just use this as a pointer here. So that not all charges are at the same distance. And that is not the situation that we're describing here. Here we're describing a situation where the charges are all concentrated at a point, so every bit of the charge, every bit of this charge is at the same distance from every bit of this charge. With the tape, charges are distributed again over the whole length of the tape, and some parts of the tape are closer to the other piece than others. So some charges are closer than others. In this case, nothing is closer than anything else. That is, all this charge is the same distance from every bit of this charge, and that distance we're going to call R. So R is the distance between the charges. Now F21 is going to be the force exerted by charge 2 on charge 1. Now we're assuming that these are repelling charges. The force is one of repulsion between the charges. Okay? And you've seen how to get that to happen with at least the tape. So F21 is the force exerted by charge Q2 on charge Q1. F12 is the force exerted by charge 1 on charge 2. Okay? In this case, the forces are repulsive. Coulomb's law says that if these are point charges, then the magnitude of the two forces is equal, and that the magnitude of the forces is equal to some constant K, which turns out to be have a numerical value here that I'll discuss in a minute, times Q1 times Q2 over R squared. Now this has the effect that if you keep Q2 the same and make Q1 twice as large, that's going to double the force, right? Because it's going to double the numerator. It's going to double this product and therefore double the whole quantity. If you made both charges twice as great, then the numerator would become 4 times as great, of course, and you'd have 4 times the force. So that the force is proportional to the product of the two charges and inversely proportional to the distance between the two charges. This is much like the law of universal gravitation, Newton's law of universal gravitation. And remember the flux picture there. There's a flux picture for Coulomb's law. We're choosing to state it right now, excuse me, in algebraic form, and we'll move to the flux picture before too long. This is just like the law of gravitation. Instead of Q's, we had M's for gravitation. Instead of K, we had capital G in the law of universal gravitation. Okay, K has the magnitude 9 times 10 to the 9th Newton meter squared per Coulomb squared. The units of K have to be Newton meter squared per Coulomb squared if we're going to deal in fundamental units. That is, we want the force to come out in newtons. So K had better contain a newton. And then it had better contain whatever other units are necessary to cancel out the units of this product so that we end up with just newtons. Well, the units of the numerator are coulombs times coulombs, or coulombs squared. To cancel out the coulombs, we're going to put a coulomb squared in the denominator. The units of the denominator here are meters squared, so we're going to have a meter squared in the numerator. Thus, when we multiply K by Q1, Q2 over R squared, the meter squared and the coulomb squared will cancel out and leave us with newtons. Note the size of this constant, 9 times 10 to the 9th. And Coulomb's law also says that the forces are equal and opposite, and that the force is a force of attraction if the charges are unlike, and a force of repulsion if the charges are like. And that's the entire statement. That's one entire statement of Coulomb's law. Now there's a flux statement of Coulomb's law, and then there's a little more rigorous vector statement of Coulomb's law. A little more concise statement. It's not any more rigorous than this. This tells the whole story. One thing we got to be careful of is the definition of attraction and the definition of repulsion if we want to make this completely rigorous then. By repulsion we mean that the force is exerted along the same line, along the line that's defined by the two charges. That is, we draw a line through the two charges. The force will be along that line. If it's a force of repulsion, it'll be along the line away from the center, the central point. If it's a force of attraction, then it'll be toward. Each charge will experience a force toward the other charge along the line joining the charges.